Super. Thanks a lot for that kind introduction and for the gratuitous quote. I don't know who that's from, but I love it. Yeah, it's really great to be here in Sydney, you know, not just because I'm from here, but also I survived that thunderstorm last night. I thought the world was going to end, and you know, I'm from Sydney. I grew up kind of in Perth and spent 5 years in Brisbane. But obviously I've been in the UK and California where you don't have thunderstorms for too long to not panic about that. I just want to tell you what we've been up to at PsiQuantum for the last 7 years. My co-founder Pete said, people want to know what you did with $1 billion, you know, like you got to tell them. And so I'm going to have to go fast because I've got a lot of material to get through here. Many photos of very expensive sports cars, Malibu mansions, etc. So just bear with me, it's going to be high speed. I'm just going to talk to you about, you know, yeah, essentially progress that we've made on the technology. I'm not going to say very much about the architecture. I'll say a little bit, but the reason that I'm not doing that is because I have a limited amount of time, which is reducing by the second here. And because we've talked about it and we've published a bunch of papers on this topic, and if you want to really understand how it's going to work, you'll need to look at these papers here. Okay, so PsiQuantum, just by way of background, we're a Silicon Valley based startup. You know, most of our people are in Silicon Valley, but we've got a handful of people around the world, including here in Australia. And we're just doing one thing, and we've always been doing one thing, which is to try and build a utility scale quantum computer. And indeed, the sort of founding thesis of the company was that utility would mean error correction, and that error correction would mean, you know, millions of qubits, and that photonics was a very appealing approach when you talk about doing things at that scale, and I'll elaborate on that. Before I do, some photographs of airplanes, because I mostly deal in cartoons these days, so it's exciting to be able to show actual photographs. The point here is really that these two things really do very much this, you know, the same basic trick, right? Powered flight, but you know, one is commercially valuable and one is not, and there's decades and billions of dollars between the two. Now, I would say the field of quantum computing, and particularly for us, we've sort of moved away from thinking too much about the qubits. I would contend that everyone's had qubits for decades, and they're all great. There's plenty of great ways to make qubits. Qubits are not the problem. What stands between us and useful quantum computing are these scaling challenges that I've articulated here. So, you know, is there a manufacturing capability that already exists or could soon exist that will enable you to build the system that you are targeting? And that's really an economic question more than anything else, I would say. Can you cool that system to the operating temperature that you need? So can you create enough cooling power? I would contend that any utility scale quantum computer will be extensive, so you're going to need to wire it up, and not with USB cables, but quantumly. And finally, apologies to my colleagues and other people in the electronics world, but the thing with systems is all the bits need to work, even the boring bits, and any large complex system like this will have a whole bunch of conventional control electronics in it, some of which will need to be proximate to the qubit layers, I would contend, unsurprisingly, and therefore of a compatible operating condition and a commensurate density. And so at PsiQuantum, we're not really fans of photons because they necessarily make better qubits. I would say they do make great qubits, but we're fans of photons because they really give orders of magnitude type advantages in overcoming these scaling challenges. So firstly, we can build photonic qubits in a regular semiconductor fab. Secondly, the photons effectively don't feel heat. So we do need cryogenic cooling for our single photon detectors, but those detectors can operate in the sort of several Kelvin regime and not in the millikelvin regime, which is often typical. And we have big advantages in terms of networking with photons because we can send qubits from one cryostat to the next cryostat just using conventional telecommunication optical fibers without the need for any sort of transduction from matter-based to photonic qubits. And indeed, we've demonstrated teleportation and entanglement between separate chips using this sort of approach. And finally, obviously, as we build more and more complex systems as an industry, it becomes desirable, and I would contend essential, to put complex control electronics close to the qubits themselves. And that's much easier if your qubits are intrinsically insensitive to heat, as I've just said. And just a quick sort of gift from above, as far as I'm concerned, if you take a 300 millimeter silicon wafer and you cover it with photonic components, you have of order 1 million photonic components on it. If you took another silicon wafer and you covered it with state-of-the-art transistors, you'd have around 1 trillion transistors on that wafer, and that's just about the Goldilocks density ratio of components that you're going to want to control a system. A lot of cool work has been done on this last topic here in Sydney, actually. So David Riley at Sydney and Microsoft has been sticking CMOS chips in cryogens for a while, and Andrew Durack, who is here somewhere, as well as Michelle Simmons, who is sitting right there, have both looked at what the requirements are for large-scale systems and the electronics. And I really think this is an important thing for the industry to make sure that we're addressing all of these challenges and addressing them very seriously, like extrapolating from what we understand today to what would really be required. And I just want to highlight one of the advantages that I would see comes with solving that connectivity issue, so just the connectivity. And it turns out that we can exploit connectivity in a number of powerful ways, and this is just one example here where we had a breakthrough in our architecture which reduces the runtime for fault-tolerant algorithms by about 50x by exploiting the non-local connections that you can realize with a fiber. And so that means that with about 1,000 resource state generators, which I'll define in the next slide somewhat, and a gigahertz clock, you would be able to crack RSA 2048 in about 9 hours. Now, a gigahertz clock is probably pretty aggressive, and probably want an order of magnitude or two further in that recipe, but I'd say this is a huge result. I encourage you to read the paper and figure out how it can be deployed in your systems, because it's universally applicable. Now, our ability at PsiQuantum to take advantage of those scaling features that I just described is really based on the photonic approach. And historically, photonic quantum computing architectures have been highly inefficient. And this is why we built a team of 25 people who've been focused for the last 7 years on reducing the overheads and dramatically increasing the thresholds in those architectures. And here's just a cartoon of how that architecture works. We call it fusion-based quantum computing. And what you see is single photons are generated here probabilistically on the left via spontaneous four-wave mixing. We send those photons into large multiplexing circuits, which generate small entangled states referred to as resource states. And what's surprising about this architecture is that we then send those entangled resources directly into a network of entangling measurements, which we call fusions. And that's the end of the story. The photons are measured and destroyed. And what we then do is feed the outcomes of those measurements forward onto the next clock cycle and run this thing a little bit like a conveyor belt, continuously generating photons on the left and measuring them on the right. And there are two features that I really want to emphasize here about this architecture. The first is that it's a constant optical depth. So each photon travels through a fixed number of optical components during its very short lifetime, and that number of components is small, no matter how big a system that you build. That's obviously crucial if you want to avoid accumulating optical loss on the photons, as that would rapidly break your loss thresholds. And secondly, while this thing can be run, in principle, on coherent computations on hundreds of logical qubits for hours or days or whatever, the largest entangled state that you ever actually produce physically is of order, tens of qubits in size. And that means that while we do have to do very aggressive multiplexing, we're never trying to multiplex to 1 million qubits, for example. That's a sort of a commonly held misapprehension. You need to multiplex to tens of qubits. And so the way we think about it is once you've got those resource states up and running, you're sort of off to the races, as it were. And I just want to say something on the topic of technological maturity in the context of the architecture, and then I'll move on to the hardware. The picture of the architecture that I showed you obviously hides a ton of complexity, and if you were to look under the hood, you'd find a complex recipe incorporating probably hundreds of new results in entangled resource state generation, multiplexing methods, error correction, et cetera, and they've been deployed by our team over the last 7 years into that architecture. Many of those you can see in those references that I described before. But the point here is that this complexity is necessary to make the architecture for optical quantum computing practical in terms of the footprint, and especially to make it resilient to error. And anytime you encounter something that's really this complex, as a technical person, or any person indeed, you should very well ask, will it really function as expected under realistic multivariate error models? And so we took that very seriously from the beginning, and we're now able to take 25 different sources of errors, so waveguide loss, dispersion, detected dark counts, and so on, and carry them through a multi-scale model at various layers of abstraction, from the basic photonic components all the way up to logical gate operations. And at the low level of abstraction, many of the input rates, error rates, are now informed by vast quantities of data that are coming from our testers, which I'll show you about in a moment. And on the right, of course, nobody has ever built systems of that scale, and so extrapolation is required. But we believe that the depth and extensiveness of this modeling framework that I'm sort of describing to you here is really unprecedented in quantum computing, and together with some convenient coincidences like the fact that photons don't interact with one another, these models are giving us really good confidence that our systems are going to hold up to these complex set of errors as we scale. And in fact, recent demonstrations of some of our more complex systems are already pushing the envelope of system-level experimental validation towards the right in this diagram. So I'm hoping to be able to share with you some more of that later this year. And given my history over the last 7 years, I expect that will be here in Australia, because I've given 4 scientific talks since starting PsyQuantum, I think. 3 of them have been here in Australia, so stay tuned for that one. So here onto the hardware. This is a map showing you how we're going to go about instantiating that architecture that I just described. So obviously we take a small number of photonic components here on the left. Most of these are actually classical components like waveguides and splitters and so on. A few of them are quantum components like single photon detectors. They get lithographically fabricated into a silicon chip using a stack of materials that you see depicted here. Those photonic chips then get packaged optically and electrically into what you can think of as a kind of motherboard. Some of those motherboards need to run at room temperature, some of them at cryogenic temperature. We then need to package a whole bunch of those boards into what you can see towards the right-hand side here, which is a kind of cryogenic cabinet or rack, a bit like a cryogenic 19-inch rack, if you like. And we're going to need many of those racks networked together with conventional optical fiber in a large facility to deliver useful applications. So that's a sort of high-level cartoon map of what we're building, and I'll talk a bunch more about that. As an organization, PsyQuantum has made thousands of wafers of silicon and millions of components. So we've got the left-hand side pretty well covered. We've built pretty large numbers of these board level assemblies, and we haven't demonstrated one of these cabinets yet, but you can see that it's under construction there, and again, more news on that soon. So that gives you a sort of sense at a high level of where we're at. And then just sort of quickly, a quick overview of what we need. When we founded this company 7 years ago, my co-founders and I, we'd been in the academic research world for a long time, and collaborating with one another, as well as the wider quantum computing community, including here in Australia. We'd sort of had an approximate sketch of the architecture that I just showed you in mind, but nothing like the level of detail that we now have. And we had demonstrated lots of small systems of entangled photons, qubits, state tomography, process tomography, etc. As far as I know, we had the first quantum processor on the internet about a decade ago. Together with our colleagues at Harvard, we invented that variational quantum eigensolver and demonstrated it on a chip also a decade ago. And we had a lot of time, spent a lot of time, had a lot of fun, published some papers and so on. But all of that time, we knew that there were really much bigger, more expensive, hard engineering problems that really needed to be solved to deliver on the promise of photonic quantum computing. And I've enumerated them here, and I'm not going to go through them in any sort of detail. I'll let you read them at your leisure in the remaining 100 milliseconds before I advance the slide, so that I can sort of take a look at what happens when you take that scaling issue very seriously in the context of just one component. So here you see a single photon nanowire detector. So you've got a waveguide here, the photon traveling along in the waveguide, a nanowire above that waveguide, and the way this operates is you cool that nanowire to well below its critical temperature, you current bias it to just below its critical current, such that the absorption of a single photon into that wire creates a local resistive hotspot. That supercurrent diverts around the hotspot, drives the whole thing normal, and in a kind of amplification process you get a very fast voltage spike that you can read out. And these are beautiful devices in every regard in terms of their properties, and can be made in principle 100% efficient. And their only drawback, I would say, is that they need cryogenic operation in the sort of Kelvin regime. And the thing is that if we're going to build a photonic quantum computer, we're going to need millions of these things. And it was really our sort of part of our founding thesis of the organization. There's only really one way that we're going to be able to build millions of those things, and that's in a tier one semiconductor fab. And there's not many of those around. You've got TSMC, Global Foundries, Samsung, Intel are sort of getting into the foundry business, maybe a couple of others that you could argue could also do this sort of thing, but not a lot of them around. And it's been my conviction, and I'm not alone in it, that unless we leverage that 50 years of development and $1 trillion that went into that industry, it's going to be very hard, and indeed probably won't happen in my lifetime. And this was indeed, an idea that was rampant at UNSW when I was there, and still is, for good reason. Another thing that I want to say that's sort of overlooked in this story and underappreciated is in quantum computing generally is testing. So, I would say that if you want to make a million qubit system, you're probably going to have to build billions of components along the way and test billions of components along the way. And if testing each of those components takes you an hour, then it's going to be a very slow process. And so we're really lucky that in a photonic system, the things that go wrong in a quantum computer are predominantly classical things and can be characterized at room temperature using robots like this one here. And this has allowed us to test millions of devices in a completely automated fashion. There's still a whole bunch of cryogenic tests that we have to do, but this really sort of takes the edge off, if you like, that you can do so much at room temperature. We have 2 of these systems running around the clock now. We have another 4 on order, and when the first of these arrived, you see it takes a cassette of 25 silicon wafers, the same cassette that's used in a tier 1 fab, and it just auto loads them into the system and so on. I did a back of the envelope calculation when the first one of these arrived, and I estimated that it does the job of about 100,000 graduate students. So within an order of magnitude. Now, let's have a look what's going on inside one of those superconducting devices. So here you see the waveguide. It's a few hundred nanometers across. You see the nanowire on top of this. And this image is the result of a 500-step manufacturing process that we use to manufacture a 25-layer stack on a 300 millimeter wafer that we stood up at Global Foundries pretty much from scratch. What I just want to now show you, if I can get this animation to work, is that if we zoom in a bit on this device, you can see a single photon detector on top of that waveguide now. You can also see a whole bunch of metal. That metal is there because the laser light that we shine into the chip is about 1 trillion times more intense than the single photon that we detect on the chip. So there's an optical dynamic range of about 120 dB, for those who talk in dB. You're also seeing cross-sections here from those chips, and I would say this is really what you're paying for at somewhere like Global Foundries to achieve this level of control over the critical dimensions, the integration, the line edge roughness, the process control, etc. And with something that's this novel and complex, there's as I say, there's really few places that you can do that. And here you see that the full chips now that are 25 millimeters on the side going into an off-the-shelf cryostat operating at a few Kelvin, and that's good enough for us to prototype the packaging as well as the device performance. But as I mentioned and will elaborate on, we're moving to much more advanced cryo systems. And for context, this off-the-shelf system gives you about a watt of heat dissipation, which is about 1,000 times more cooling power than you typically get in a dilution refrigerator in the millikelvin regime. So that gives you some latitude. All right, and just to emphasize, the performance that you get, which is again what I say is that what you pay for is the performance and yield, etc. And you can kind of see that represented in these wafer maps here. So on the top left, if you were to measure the width of one of those nanowires between two different wafers, you would find that they were the same to within a few nanometers. And if you were to measure the film thickness between two different wafers, they'd be the same to within about an angstrom. And that's really the kind of process control that we think you need in order to build a utility scale quantum computer. And that process control indeed does translate into device performance. So you can see that the intrinsic efficiency of the nanowire itself is really close to 100%. You can also see data on this slide at the bottom here from number resolving detectors. We'd like to be able to count up to 3 photons in a single mode. We've built devices that can do that, and you can see about a 95% separation between the different number buckets there. But now I want to just highlight that most of our detectors that we've built so far are on silicon waveguides, and silicon is quite lossy, optically lossy, and this limits our system efficiency, which really needs to be in the ballpark of 99% system efficiency. And so one of the big investments that we've made recently is making a switch from silicon waveguides to silicon nitride waveguides, which can be much lower loss. But silicon nitride is hard to work with, as you can see from these central images. These are the pictures that people don't typically show of cracks across entire wafers. There's lots of grind here. There's expensive hard work, and we've been through hundreds of wafers, a lot of pain and suffering to get to the point that we're at now. But I would contend that we have silicon nitride nicely under control here. So at the top of this chart here, you see the best waveguide loss performance that we've seen from silicon waveguides. At the bottom, you see the target here, and in between, you see progress from that 2 years of hard work to bring down the losses in silicon nitride waveguides. You can see we're not there yet, but I'm very encouraged by these results. Okay, so quickly on the photon generation. So for the removal of doubt, we don't use any sort of single emitter sources, NVs or quantum dots or something. We just use spontaneous 4-wave mixing in silicon. And with the sort of simple ring resonator shown on the left here, you can achieve about a 90% purity. That's fundamentally intrinsically limited. With these more advanced designs, we've demonstrated 99.5% purity, and then going forward, we're going to use these more complex arrays of ring resonators where we expect to be able to hit about 99.9% purity. And if you want to talk about that topic, find Dylan, who's somewhere in the audience, and then brace yourself. One of the things that you've probably already heard about in the context of various different approaches to quantum computing is the need for connectivity that I highlighted before. However you build your qubits, I would say that a utility scale system is probably going to need to get light in and out of optical waveguides with incredibly high efficiency. And the telecommunication industry does this today, but with nowhere near the sort of efficiency that you need for fault tolerance. And so at PsiQuantum, we've made a big investment into solving this problem. We've developed new designs for an edge coupler. It's a manufacturable design that's compatible with high volume manufacturing processes, and we've built these devices. This is not that device, this is a different type of coupler. It's just a regular coupler butted up against a waveguide here. And the task is illustrated here, which is that you want to get light out of that waveguide and into that fiber with around 99% efficiency, and that's tough. Here's some early data from our most recent devices where you can see that we're in the ballpark of 98% efficiency, so there's still a lot of work to do here in turning this into a manufacturable assembly that we can build in in really large numbers. But the fact that we can do it at all is very encouraging to me. So more work ongoing on that. And then, I just want to say something here about multiplexing. So as with every approach to quantum computing, we haven't seen thousands of photonic qubits as yet. And the reason that we haven't seen thousands of photonic qubits is because of the need for multiplexing. So a photonic quantum computer, pretty much everything is non-deterministic. So specifically the single photon generation as well as the entangling operations are non-deterministic. And obviously error correcting codes have some leniency, but whilst they're very resilient to failure, it's nonetheless absolutely necessary to do trial until success. So you have to take your non-deterministic operations, do them a bunch of times and pick the successful outcomes and move off of this exponential decay onto something that's a lot more tractable to deal with. And of course, you only need to multiplex up to the tolerance of the error correcting code that you're using, and the scale of that multiplexing just needs to be to the biggest subsystem that you required. And as I said earlier, the largest entangled resource states that we ever instantiate in our current architecture for optical quantum computing are on the order of 20 to 30 qubits. And that's independent of the problem size. So no matter how many logical qubits or gate operations we're targeting, that stays constant. So that's the good news. That said, we obviously need to do very high performance multiplexing. And if you ask me to point to a single technical challenge that was holding back photonic quantum computing, don't bother doing that in the Q&A because I'm going to answer it right now. It's multiplexing. And what you have to do is take a whole bunch of non-deterministic operations, run them in parallel, and then you want to pick one of the successful ones. So that's the sketch here, and that picking gets done with an optical switch here. And that optical switch, of course, is just a classical device. There's nothing quantum about it. It's just routing light around on the chip. But the optical phase shifting material that you needs to be really, really good for fault tolerance. And so you can buy devices like this off the shelf. Many of them use lithium niobate, most of them. And the electro-optic coefficient of lithium niobate is about 20 picometers per volt. And we need something that's way better than that, from a materials perspective. And there's a few options, PZT, polymers. And I would say that we sort of swung for the fences, as we like to say in the US, but it works perfectly down here as well. And we picked the strongest electro-optic material known to mankind, to humankind, and that's BTO. And that has an optical electro-optic coefficient of around 1,000 picometers per volt. And the device performance goes with the square of that electro-optic coefficient. So the impact can be very profound indeed. Now, once again, the task here is very much like what we already did with the superconducting detectors, but it's very big and expensive. Although it looks very easy when you just draw it as a cartoon. All you got to do is, put a thin film down, pattern it lithographically, and then incorporate it into the stack. It's actually really hard, and the hardest bit is this first part. This is the piece that scares engineers because it's material science, and my co-founder Pete likes to say, to those of you not familiar with material science, it's a bit like French patisserie. You get a whole bunch of ingredients, you put them all together, you chuck it in the oven, and out comes a big burnt pile of crap most of the time. We were lucky, so we took the problem pretty seriously. We built a big facility in San Jose. There's 5 clean rooms in this facility. One of those clean rooms has what we think is the biggest molecular beam epitaxy tool that's ever been built. It's a 300 millimeter MBE system. It's also highly industrialized, as you can see in this video. So often you think of sort of research grade stuff when you talk about MBE, but as you can see, it's got one of those cassettes of 25 wafers and auto loaders, etc. in it. The robot moves those wafers through the chamber, and inside that chamber, just for your gratuitous satisfaction, there's molten titanium at a few thousand degrees Celsius, and there's also liquid helium at a few degrees Kelvin. So it's a pretty extreme piece of equipment. And what's interesting to me is that it's clean enough that we can take a box of those wafers out of that tool in our facility in San Jose and FedEx it off to Global Foundries and integrate it into their much more mature manufacturing flow. So that's a big requirement that we can just directly transfer between them. And we're doing that. So we've built, 300 millimeter wafers of BTO. We've shipped them to Global Foundries. We're doing lithography on it. And as you can see, it's getting integrated into that Global Foundries environment. And I kind of, I'm really proud of the work that we have done as an organization here and the risk that we took in doing that. We spent a ton of money doing this and spent a lot of hard hours, and it was really uncertain. It could have been the case that we spent months looking at that burnt trash coming out of here, and banging our heads against the wall. My daughter, who's 14, she recently tried to make croissants. Anyone made croissants? It's really quite hard. Some genius who was Austrian, I think, got it into their head, not enough butter in the pastry. How do I get more butter in there? It's a bit like our single photon source. There's a no-go theorem about how much butter you can actually, and it turns out if you could layer it and wrap the butter and freeze it, and it's madness. Anyway, she told me that you can't expect to get anything like a croissant out the first several times you do it. And indeed, she did not get anything like a croissant out of it. But the good news for PsiQuantum is that we did. We got some very nice croissants out of this thing. So the first wafer that we got in Q1 last year had an electro-optic coefficient of 350 picometers per volt. By the second quarter, we'd improved that to 450 picometers per volt, and the very most recent wafers were up to 1,000 picometers per volt, which is as strong as you can reasonably expect. Now, I want to highlight that there's still a ton of work to do on the film uniformity, the volume of wafers that we can produce, the yield, etc. But so it's by no means a solved problem. There's still a ton of work to do, but we're very happy, obviously, as you can imagine, to be getting these films with this performance out. And of course, we've built full switches with BTO. We've operated them at cryogenic temperatures. We've operated them at gigahertz speed, and this is a highlight for us, and it's been long-standing. How do you make the optical switch? Well, I would contend that we pretty much have the answer now. What's this about? Okay, so if you look at the literature, there's many demonstrations of qubits over the decades in photonics, state tomography, entanglement, and so on. But as is always the sort of case in these academic demonstrations, they're always leaving something out. there's always something that's sort of swept under the carpet, you know, like the sources are separate, or the detectors, or the switch, or something or other. And, you know, we really can't afford to do that, obviously, if we're building a real system. And we have to solve all of those problems simultaneously in the single system. And I want to show you quickly some work that we've been doing towards that. So this is single qubit tomography experiments and 2-photon interference experiments, where we're bringing much more of that unpleasantness, if you like, onto the chip. So specifically, there's fully integrated single photon sources, superconducting single photon detectors. The filtering is done off chip in this case, which is again 120 dB of filtering, and thermal heaters are on the chip. So we actually have thermal heaters, which we use as phase shifters, and when we operate them, they're operating close to room temperature, and we dissipate about half a watt of heat through those phase shifters, despite the fact that the whole chip is at cryogenic temperature. And soon those phase shifters will be replaced with that BTO that I just showed you before. But you know, they're actually, these thermal ones are a pretty good stand-in for those gigahertz BTO switches, and I think it still blows my mind that, you know, you can have a single chip with superconducting single photon detectors operating at a few Kelvin next to a room temperature thermal phase shifter. I'm being hurried up here, and I think I'm almost done. It works very nicely. So this is single qubit tomography data where we see a 99.96% single photon state preparation fidelity and a 4 nines single qubit gate fidelity. So that's encouraging. What's more interesting than the numbers to me is the system that we've built. I won't talk about quantum interference, but that's the driving force of our architecture. So you send 2 photons into a 50-50 beam splitter, and they both come out one or other output, but not both outputs, and you observe that like this, where you delay one with respect to the other, and when there's no delay, there's no probability of detecting the 2 photons at the 2 outputs. The depth of this dip, how close it goes to zero, measured as the visibility, is really the important driver here, and in this case, we're able to see 99% visibility. The systems that I've shown you have hundreds of wires. The systems we're building now have thousands of wires, and obviously we need to bring the CMOS closer and closer to the qubits. As I said, this is a challenge that's industry-wide, is being addressed, I think, here in Sydney in a great way. We've built a Cryo-CMOS ASIC. It's a 22 nanometer CMOS process, same transistors that are in Bluetooth devices. It has 750 million transistors. It runs hundreds of tuner drivers and hundreds of detector readout circuits. And you can see it's packaged up with a photonic chip with superconducting detectors and single photon sources. And you take that whole assembly, you stick it in a cryostat, and then you pray. And you pray that it works, and guess what, it does. And I don't have time to tell you too much about that, but we are working on our next generation of these things. It's going to have 32 gigabit SerDes on it, half a gigabyte of SRAM, so that's charging ahead nicely. You have to cool, as you build those bigger and bigger systems, you have to cool them. I've shown you the sort of 1 watt of cooling power in the commercial systems. This thing's getting welded up as we speak. These cabinets need to be networked together using conventional telecommunications fibers. And this is one thing that I think is really mad, is that they have drawers in the cryogenic cabinets. So people in this company have done a lot of things where I've said, really, are you sure that's going to work? And time and again, they've said yes, and they've been right. And this is one that I'm looking forward to being wrong about again, but with my skepticism. One thing that I just want to highlight is that the detectors, as I've said, are the only thing that needs to be cold in this system. So we're making a big investment into an alternative material that would allow us to go much higher temperature. I can tell you that it's not YB-SUR. It's not a type 2 superconductor. I'm not going to tell you what it is. Maybe next time I give a scientific talk, which I say should be in Australia by my reckoning. I can say that it's a manufacturable metal superconductor, and if we get it to work, it would allow us to go to much higher temperatures. And here you see the progress that we're pushing our transition temperature up to around 30 Kelvin, and this could make make the cryogenics a whole lot more practical and cheaper. I want to be clear that the niobium nitride that we're currently using will get us there. We just need to build more infrastructure at more cost. And to put those, put the numbers in context when it comes to cryogenics, this is Stanford's linear accelerator, walking distance from where I am in Palo Alto. It does about 10 kilowatts of cryogenic cooling power at 10 Kelvin. It was built by PsiQuantum's Chief Product Officer, Nicholas Kellers, in his previous role as Chief Engineer at SLAC. It's the type of system that we're going to need for a utility scale quantum computing. And on the one hand, it's a big, scary industrial facility, but on the other hand, it exists. There's a photograph of it right there. And that's my kind of technology, ones that exist already. And that brings me to a conclusion, which is to say that our short history as an organization is that we spent 20 years prior to the company forming in the scientific world trying to answer that question, is there a path to leveraging that semiconductor industry? We spent the last 7 years and hundreds of millions of dollars actually getting into that industry and getting to the point where we're essentially mass manufacturing quantum chips in a tier 1 fab. And now we spend a lot of time thinking about the cement and steel and kilometers of optical fiber that you're going to need to build a facility like the one that I've sketched here. So with that, I shall thank you. Feel free to ask a question. I guarantee I won't know the answer. Don't mistake me for a professor of physics.
That was a stonking talk, Jeremy. Thanks so much. Loved the croissant analogy as well. I think we could all come home to that one with our failed kitchen disasters during COVID. We've got time for 2 questions. So do we have one in the room? Very quickly, if you can just pop your hand up. Yes, there's a question. If we can just get the microphone in the centre there. Keep your hand up, please. Thanks. And just your name and question.
Hello, thank you for this wonderful talk. So I am Neil from University of Melbourne. So I understand that PsiQuantum is using discrete variable quantum computing. So what are your thoughts on using continuous variable quantum computing, and what are the merits and demerits as opposed to the current technology being developed?
And we don't have 45 minutes for the answer.
Not 45 minutes. No. I think, so I've spent a lot of my time working on discrete variable photonic quantum computing, as you say, and I'm far from an expert on continuous variable. I have done a little bit of work with Akira Furusawa on this topic and published a few papers, and he's always advocating to me that you can do some things deterministically. He likes a hybrid approach, right, where you can do some things deterministically in one or the other, and you can hybridize them. I'm always skeptical about hybridization because you either get the best of both worlds or the worst of both worlds. But I think there's some really exciting and interesting advantages, particularly about what operations become deterministic. But there's no doubt people here who are more expert than me that you should ask that question on.
And can I say either the best of or the worst of is a very binary approach for a quantum kind of thing.
Well, like if you take a quantum system that you're going to use as a memory and a different quantum system that you're going to use as a processor, because this one's very long-lived and this one's very fast, and then you try and hybridize them, that's kind of an appealing idea, but they're freaking hard enough in and of themselves. And so
Double
you're also,
the croissant.
I mean, it's not a scientific proof,
okay.
But it really is. So, yeah.
Great. Do we have one more question in the room, or we've got a couple coming in here? Your choice of the. Oh, here we go. Yes. Can I just shout loud? No. But while we're getting the microphone to you, how are the photonic qubits initialized?
So you just inject a single photon into one of 2 waveguides, and then you.
Easy peasy. Excellent use of time.
Okay, so so fascinating technology also, anyone who's working. And then also all the platforms leverage CMOS technologies one way to the other. And I think the one part that maybe I'm not personally familiar with is this fiber coupling. I know it's extremely important, and then there are not many studies. And what is your strategy to scale up to manufacture that part of the fiber coupling from the chip to the wire?
Do you know anything about this topic, and do you want to tell?
I know a little bit of the topic, and that's why I'm asking. Yes.
Okay. Yeah. Well, let's talk afterwards for sure.
Give you time to Google it.
No, well, I mean, I've said everything that I can say on that topic. So I've shown you 98% coupling efficiency between waveguides and fiber. That's using a pretty clever design that we've come up with. We need to scale that up. So this is a kind of laboratory demonstration. You don't have to, the fiber to chip coupling isn't at the scale of the qubits themselves, right? So you need to be able to get that into a contract manufacturer, system assembly house type, people who can do hundreds of fiber attach and get those things working. And we're not there yet, but we have some good ideas. If you have some too, please let me know.
Jeremy, thank you so much. That was a fantastic keynote and great and quick Q&A.